All right. Good afternoon, everyone. So, bago tayo pumunta sa weekend, tatapusin muna natin yung module number 3 so that we will be able to finish Lab XR 1.2 na on Monday. All right. So, in the previous meetings, we talked about two iterative processes in finding the roots of a nonlinear function. We talked about the Newton-Raphson method na maganda siyang i-implement at saka mabilis yung convergence niya. It has quadratic convergence, though the convergence is not guaranteed. Pero if you will be able to select an initial guess that is close enough to the actual root, then yeah, mabilis magko-converge yung method kasi nga quadratic yung convergence niya. But there are some issues involved in implementing the Newton-Raphson method. Lalo na kapag ka nag-zero yung derivative. So if you are hitting a relative maximum or a relative minimum or somewhere near them na yung derivative ay almost nag-zero or it is zero at machine precision, then magkakaproblema yung iteration. So to compensate for that, pwede nating i-sacrifice yung kaunting rate of convergence in favor of a less likelihood of coming up with zero divisor in your iteration formula. Yun yung sa secant method, which resembles what we did with the regular falsi method, right? So two guesses sa secant method, you find a line passing through those two guesses, and then the x-intercept of that line will serve as our estimate for the root. Now, mas maliit yung chance na magkaroon ka ng zero divisor in the iteration process, kaya lang it comes out a price. So nabawasan ng around 0.4 yung order of convergence kasi o yung rate of convergence kasi ang rate niya lang ay golden ratio. It's around 1.618. Okay? So those are iterative processes, and now we will venture into some more generic type of iterative processes. And you will realize that the Newton-Raphson and the secant method are special cases nitong tinatawag nating mga fixed point iterations. All right? So let's begin with looking at what are fixed points and what are fixed point iterations. Definition 1. Okay? So a real number P is a fixed point of a function f if and only if p is equal to f of p. So ibig sabihin, fixed point siya kapag ang function value niya under f ay yung sarili niya. So parang invariant siya, hindi siya nababago dun sa function f. You plug it in into your function f and you get back the number again. Alright? Yan yung mga tinatawag nating fixed point. Kaya fixed, hindi nababago yung value niya pagka nag-undergo siya ng function evaluation. Alright? And then if you have a recursion formula of the form given in equation 14, x sub n plus 1 equals the function value of your previous iterate, evaluate at under f, then that's what we call a fixed point iteration. Okay? So kung meron kang function f, yung new iterate ay function value lang ng previous iterate, then isa siyang fixed point iteration. And here you will see that the Newton-Raphson and the secant method follows the fixed point iteration form given in equation 3.14. Lalo na yung Newton-Raphson. Kasi remember sa Newton-Raphson, ang formula natin ay x sub n plus 1 equals x sub n minus f of x over, or f of x sub n over f prime of x sub n. All right? So we can just define g of x to be x minus f of x over f prime of x, and this would be our iteration. And then we see that indeed Newton-Raphson is a fixed point iteration. So given ka ng isang function f, dinidefine mo yung function g to be this guy, all right? X minus f of x over f prime of x. So ibig sabihin, pwede nating masulat yung Newton-Raphson iteration in this way, g of x sub n. So indeed, talagang yung Newton-Raphson ay isang klase ng fixed point iteration. All right? And the secant method can also be looked at as fixed point iteration. Kailangan nga lang nating i-modify ng kaunti yung equation 3.14 to allow the recursion to use two previous values. All right? So magiging function nga lang siya of two variables, x sub n and x sub n minus 1. Okay? So two simple terms, fixed points and fixed point iterations. Okay. So let's look at some specific examples. All right. Example 4. Si square root of 5 ay isang fixed point na mga sumusunod na function. Si function f, 5 plus x minus x squared. Well, it's easy to check. Just plug in root 5, and you'll have 5 plus root 5 minus root 5 squared. So it's going to be 5 plus root 5 minus 5 equals root 5. Since the function value of root 5 under the function f is itself, then we say root 5 is a fixed point of the function f. All right. Same thing goes for g of x. If you plug in root 5 in here, then you can find a fixed point. All right. You will find that root 5 is a fixed point of g. Ganun din kay h, ganun din kay j. Okay. Now, I hope so far everything is good, right? Paano kaya pag binigyan ko kayo ng k? Paano nyo masosolve yung fixed point ng isang function k? So meron kayong function, okay? Function k of x. And then if I ask you to find a fixed point, how will you do that? Anyone? For bonus points? Paano natin nako-compute yung fixed points? Or halimbawa ito, paano ko nalaman na si root 5 ay isang fixed point ng function f? Ano yung pwede kong gawin para ma-compute yung mga fixed points? Anyone? Feeling ko live naman ako, no? At naririnig nyo ako, ayaw nyo lang sumagot. Kasi nakikita ko yung screen ko yung sinishare kong screen in my laptop. So, any volunteer? Grabe, snobbish talaga kayo, no? Friday na Friday pa naman. So, dapat full of energy na kayo kasi weekend na bukas. Though ako ay marami pa rin dapat gawin. Dahil matatapos na ngayon ng Module 3, so dapat matapos ko na rin isulat yung Module 4. Tapos may utang pa ako sa mga nagwa 155. Hindi ko pa nabibigay yung homework nila. So, yeah. How do I solve for fixed points? How did I come up with a root 5 dito sa function f? Oh, nakita ko yon. Jericho?
Sir, i-equate po ba siya sa x, yung 5 plus x minus x squared po?
All right, that's perfect. Thank you, Jericho. Yeah, na-compute siya, ginawa ko lang ay k of x equals x, and then I solve for x. So same thing here, 5 plus x minus x squared. Equate mo lang siya kay x. Makukuha mo yung x na ang function value ay equals sa sarili niya. All right? So that's how you compute for fixed points. But of course, that would be a big problem. Kasi nga, lalo na kung malaki yung degree o hindi polynomial yung function involved. Yun nga yung problema natin no, paghanap ng mga roots. So halimbawa, meron kang arctangent of x plus hyperbolic cosine of x plus e to the x. Tapos kukunan mo siya ng fixed point. So magiging root finding problem na siya in a sense na yung arctan of x minus arccosh halimbawa, or sorry, cosh of x minus e to the x. Pag hanapin mo yung fixed point niya, i-equate mo yan kay x. So mahirap siyang isolve kasi non-linear to. Wala tayong mga techniques usually on how to solve solutions to transcendental equations, right? Pwede mo siyang gawing root finding, problem. Mag-subtract ka lang ng x from both sides. So basically, you're looking for the root of this guy. Tapos ito yung ginagawa natin since we started Math 175, looking for techniques on how to solve equations like this. Kaya makikita nyo, mukhang ang kakalabasan din talaga nitong mga fixed point iterations ay solving for roots of nonlinear equations, all right? Or nonlinear functions. Okay, so but that's how you find fixed points for at least elementary functions. So, halimbawa, 5 over x, equate mo lang yan kay x, makukuha mo 5 equals x squared, take the square root of both sides, you'll get plus or minus root 5. So, hindi lang pala si root 5 ang fixed point ni 5 over x, pati si negative root of 5. All right? And so on. So that's how we compute for fixed points. But again, it's not realistic to compute fixed points for every function, especially for transcendental or high degree polynomials. right? Now, in example 5, we look at some fixed point iterations. So, ang ginawa ko lang dito, si x sub n plus 1, ay ko-computing ko lang as the function value of x sub n. The value of x sub n under the function f given here. All right? So, para maging fixed point iteration na siya. All right? Of course, you will need to give a starting point, so an initial guess x sub 0 or initial condition x sub 0. But after that, yeah, magiging smooth na yung proseso kasi para ma-compute si x sub 1, ipla-plug in mo lang si x sub 0 dito. Para ma-compute mo si x sub 2, ipla-plug in mo lang si x sub 1, and so on. So if you, I hope you can imagine that if I ask you to do a fixed point iteration, kayang-kaya nyo itong gawin sa Excel. Kasi isang higit lang ng formula, kung naka-vertical table kayo, i-click-click nyo lang yung nasa taas. Tapos yun yung magiging function. Yun yung ipla-plug in niya doon sa given function. Alright? So, thank you, Ezekiel. Sumagot pala si Ezekiel, kaya lang ngayon lang siya lumabas sa chat ko. Super lag ba ako? Ngayon ko lang nakita yung sagot ni Ezekiel. So, hopefully, hindi naman ganun ka-lag. Can you let me know? So, sa iba kong klase kahapon, I was forced to use my mobile data na. Okay, thank you, Charles. All right. So, medyo delay nga lang yung messages yata sa chat. Okay. So, all right. So, fixed point iterations. Tapos, yeah. Bakit maganda yung fixed point iteration? So, we can kind of think, yeah, magandang property yung pagiging isang fixed point. Kasi, nare-retain yung identity ng input dun sa function. Pero ano yung kahalagahan o ano yung maganda sa fixed point iterations? At ano yung, bakit siya tinawag na fixed point iteration? Kasi pag nag-iterate ka naman, well, magpa-plug in ako ng previous values, pero bakit siya binigyan ng special na pangalan? Bakit siya tinawag na fixed point iteration? And the answer is in Theorem 3.3. Now, sorry. Now, it says that if you have a continuous function, all right, napaka-simple ng assumption, continuous function, and you have a sequence of x sub n's that is produced by a fixed point iteration. Now, it says here that if that sequence will converge to a number p, then p is a fixed point of f. Ito yung connection. Bakit tinawag na fixed point iteration? You might be thinking out of the blue, bakit siya tinawag na fixed point iteration? Wala naman siyang kinalaman sa mga fixed points. Ito yung kasagutan, Theorem 3.3. As long as your function is continuous, and if the sequence of the sequence produced by a fixed point iteration converges, then sure tayo kung saan siya nag-converge, yun ay isang fixed point. All right? Now, just a little bit of technicality here. A fixed point iteration is not guaranteed to converge. Hindi necessary na convergent ang mga sequence na na-produce ng isang fixed point iteration. Pero, pag sinwerte ka, tapos nag-converge siya, sure tayo na magko-converge siya sa isang fixed point ng function f. Right? As long as, again, f is continuous. And you will see in the proof why continuity plays a very important role in this result. So let's read the proof. Okay, now, again, part ng assumption na convergent yung fixed point iteration. Kasi nga, hindi siya lagi nagko-converge. Pero, pag nag-converge siya, papunta kay P, then, alam natin, in the language of analysis or calculus, limit of x sub n as n approaches infinity ay equal kay P. Yun yung ibig sabihin ng convergence. But I can play a little bit with the subscript. Okay? Basta imagine niyo, okay, di ba sa limit parang nagsasubstitute lang tayo nung nasa ilalim. Though technically, hindi ganun yung nangyayari. Baka magagalit yung mga calculus teachers niyo sa akin. Pero parang ganun yung nangyayari, especially if your function is continuous, right? So parang imagine mo, okay, parang x sub infinity yung nangyayari. Lagyan ko ng quotation, x sub infinity. So yung x sub infinity, quote-unquote, ay equal kay p. Now, pag dinagdagan ko ng isa yung subscript, magiging x sub infinity pa rin yan. Kasi pag nagdagdag ako ng isa sa very large number, it will still be that very large number. Right? Tapos parang ito ay, in the long run, habang lumalaki si n, papalapit ako ng papalapit kay p. Pero dito, habang palaki ng palaki si n plus 1 palaki pa rin ng palaki. So you can think of it as x sub infinity pa rin, and it will converge to p as well. All right. So these are two ways of interpreting the convergence of x sub n to the number p. And remember, what we want to show here is that given f is continuous, then p would be a fixed point. Gusto kong ipakita yung f of p ay equal kay p. Right? Now, I will use continuity and the fact that sabi nga yung x sub n ay na-compute galing sa fixed point iteration. Remember, a fixed point iteration is something of this form. X sub n plus 1 is equal to f of x sub n. Now, paano papasok yung continuity? Well, since I want to show that p is a fixed point, I want to show that f of p is equal to p. So let's now try to compute f of p. So f of p, plug in mo si p, pero si p, according to this statement, ay equal sa limit ng x sub n's. So ibig sabihin, f of limit of x sub n. All right, nothing fancy there, substitution of p as a limit. Now, dito papasok yung continuity. Pag continuous yung function, pwede mong i-interchange yung function evaluation at yung pagkuha ng limit. Remember, kapag ka continuous ang function, ibig sabihin yung function value ay equal dun sa limit. All right? And that's what allowed me to put f inside the limit, right? Instead of taking the function value of the limit, pwede kong kunin yung limit ng function values. And again, I can only do this since f is continuous. All right? Kasi ang limit ay hindi laging equal sa function value. Pero pag continuous si f, nangyayari yung equality na yon. So putting f inside the limit will give us the limit of f of x sub n as x approaches positive infinity. All right? But what is f of x sub n? Since f of x sub n defines the fixed point iteration, then f of x sub n is equal to x sub n plus 1. So this guy, the function inside the limit, can be replaced by x sub n plus 1. Right? Then I take the limit of f of x sub n plus 1 as n approaches infinity. Then according to this statement here, that is equal to p. Right? So ultimately, what we have here is that f of p is equal to p. And ito na yung pinaka-satisfying na part, drawing in a black box. Right? So indeed here we see that if your fixed point iteration converges to a number. So any questions so far? Sana ganyan lang yung mga proofs, no? Paglalaruan mo lang yung mga previous topics na Now, another cool result about fixed point iterations, ito naman yung mag-guarantee. Theorem 3.4, siya yung mag-guarantee kung kailan nagkakaroon ng fixed point. Now, I think nag-freeze yung screen ko. Yung Theorem 3.4, siya yung nasa pinakataas. Yun na rin ba nasa screens niya? Or kit, ayan, ngayon pa lang siya tumaas. Tataas pa yun ng isa. Okay, there you go. All right, so yeah, ang tanong, kailan ka nagkaka-fixed point? Kasi nga, hindi siya guaranteed lagi nagko-converge. So maganda ring malaman kung kailan nagkakaroon ng fixed point ang isang continuous function. All right? So if you have a continuous function over the interval AB, and it also happened that the function value or the function values are also in the interval AB. So dito, kapag yung function mo, ang domain niya ay closed interval AB, tapos ang range niya ay closed interval AB rin, tapos continuous siya, then that function has a fixed point in a closed interval AB. So ang kailangan lang pala, continuous function, dapat maging function siya from AB to AB, okay? Tapos continuous. Then that guarantees na meron kang fixed point doon sa closed interval AB. Now the proof uses a clever trick. Ano yung clever trick? Nag-define siya ng isang auxiliary function. Dinefine niya yung auxiliary function g of x equals x minus f of x. Okay? Tapos, gagamitin niya yung intermediate value theorem. So, tingnan natin kung paano ginamit yung IVT. Now, dahil si f daw ay continuous, kasi nga, I will use the IVT. So, requirement ng IVT, dapat continuous yung function na paggagamitan mo ng IVT. I'll use IVT on G, so I need to investigate if G is continuous, right? All we know in the assumptions is that f is continuous. Kaya lang si x, the identity function, is also continuous. The difference of two continuous functions is also continuous. So that means G is continuous as well. All right, so yun yung second sentence. And then from the assumption, we know that function values under f comes from the closed interval AB. So ibig sabihin si f of x ay between a and b inclusive. Okay? Tapos tingnan natin yung g of a. Now si g of a ay equals sa a minus f of a. Pero anong masasabi natin kay f of a? F of a is a number that is greater than, or f of a is a number that is greater than or equal to a. So, ibig sabihin, ito ay mas malaki or equal kay a. Alright? So that means g of a is less than or equal to 0. Kasi nga yung f of a, nasa-satisfy niya yung inequality na to. So definitely si g of a ay non-positive. Okay? On the other hand, if you plug in b here, g of b equals b minus f of b. But f of b is smaller than b, less than or equal siya kay b. So ibig sabihin yung f of b, the subtrahend, is less than or equal to b, so that means this is non-negative. All right? So g of b is greater than or equal to 0. Now, by the intermediate value theorem, kung yung g of a at saka g of b ay greater than or equal to 0, then we are sure that there exists an r on the closed interval AB such that g of r is equal to 0. Okay? Now, kapag ka, medyo generalized version ng IVT, kasi yung g of a ay less than or equal to 0, pag si g of a o kaya si g of b ay eksaktong 0, then r equals a or b. Alright? Pero kung pareha silang negative, kung ang g of a ay negative, tas ang g of b ay positive, ibig sabihin magkaiba yung sign ni g of a at ni g of b, continuous si g, so sure tayo na dadaan siya sa x equals 0. So meron tayong root. So in either case, you are sure that there exists an r such that g of r is equal to 0. Okay? Pero what does it mean when g of r is equal to 0? Now, I have a typo in the proof. R of r yata yung sinulat ko. Dapat g of r siya. So we know that g of r is equal to 0, but g of r can also be computed by plugging in r into this function. All right? So magiging r minus f of r equal siya kay 0. And then a little bit of manipulation will give us this guy. R is equal to f of r. So here, r is the promised fixed point of the function f. All right? So yun pala, para siya ay magkaroon ng fixed point, dapat siya ay function from AB to AB. Tapos continuous. Tapos kung continuous yung function, tapos nag-define ka ng fixed point iteration using f, then we are sure that if that function f, if that fixed point iteration converges, then it will converge to the fixed point r on that interval. Okay? So medyo maraming layers yung pagkakaroon ng fixed point iterations, and actually I'll give you more results. Paano natin magagaranti na hindi lamang may fixed point, pero yung fixed point iterations ay magko-converge. So basically we are putting together theorems 3.3 and then 3.4 into a bigger theorem, which we call the contraction mapping theorem, or CMT. The CMT is a very powerful theorem. When I took my PhD class in applied analysis, tapos sa optimization theory, tinake ko rin yata. Ito rin yung pinaka-ingrande, o ito yung pinaka-focus na theorem, the contraction mapping theorem. It's a very important theorem in applied analysis, optimization theory, even in functional analysis. All right? Kasi siya yung magsasabi kung kailan magko-converge yung mga fixed point iterations, or what are the sufficient conditions so that you will get a convergent fixed point iteration. And not just that, yung ibang parts nito magbibigay sa atin ng error estimates. Okay? So let's see what the contraction mapping theorem is telling us. Okay. Now, what are the assumptions? The premises are f and f prime must be continuous. So twice continuous dapat yung function. Ibig sabihin si f at saka si f prime ay continuous. Tapos siya ay function from AB to AB din. Okay? Domain and range ay AB. So ibig sabihin, sure tayo na meron siyang fixed point according to Theorem 3.4. And that is what part 1 of the contraction mapping theorem reiterates. So parang siya yung nasa Theorem 3.4 natin. Okay? Yeah. And then what's next? Well, aside from being a function from AB to AB, ipagpalagay natin daw na ang first derivative o ang magnitude ng first derivative ni f over the interval AB called lambda ay less than 1. So, kaya siya tinawag na contraction. Kasi ano bang ibig sabihin ng contraction? Parang pinapaliit mo, right? It's the antonym ng pag-expand. So, kino-contract natin or pinapaliit natin yung function. Kaya siya contraction kasi ina-assume natin na yung magnitude ng first derivative over the interval AB is less than 1. Ano nga ba yung derivative? The derivative tells us the rate of change of a function, right? So if the rate of change is less than 1 or the magnitude of the rate of change is less than 1, ibig sabihin, either lumalaki siya or lumiliit yung function pero at a very slow pace. Kasi less than 1 yung kanyang paglaki or pagliit. Kaya siya tinatawag na contraction. Mabagal yung pagliit niya or paglaki. Alright? Kasi nga, ina-assume natin na yung first derivative's magnitude is bounded above by the value 1. Okay. Now, then, if all of these premises are satisfied, ano yung binibigay sa atin ng contraction mapping theorem? Again, we already mentioned the result number 1. Pwedeng ginamit na lang yung theorem 3.4 dyan. Okay? Pero itong theorem part 2 says that for any initial point x sub 0 in a closed interval AB, then the fixed point iteration will converge to P. Okay? So, and then this is basically theorem 3. Theorem 3.4. Kahit na anong piliin mong initial point doon sa interval AB, sure tayo lagi na magko-converge yung fixed point iteration natin. Okay? So medyo yung theorem 3.3, sabi niya pag nag-converge, magko-converge siya sa fixed point. Pero if all these premises are satisfied, then we are sure that if we choose any initial point on the closed interval AB, guaranteed tayo na magko-converge na yung fixed point iteration. And then by theorem 3.3, dahil itong iteration na to ay nagko-converge, sure tayo magko-converge siya dun sa unique fixed point na P. All right? Now, those are two kind of easy properties to remember, all right? Medyo komplikado yung results 3 and 4. Result 3 gives us an estimate for the error on the nth iteration. Okay? Ang sabi rito, if P is the fixed point, kung saan nagko-converge yung fixed point iteration, the error on the nth iteration, so yung magnitude ng P minus Xn, gaano kalayo yung nth estimate dun sa actual limit or actual fixed point P, yun ay bounded above ng lambda to the power n over 1 minus lambda times the distance between x0 and x1. Ito nga pala yung dapat kong i-double check. Tama nga ba? X sub 0 minus x sub 1. Give me 30 seconds. Kalimutan kong i-check kanina. Nung binabasa ko siya kanina, medyo nagduda ako dun sa theorem. Let me just consult my notes. Yeah, that's right. Magnitude ng x sub 0 minus x sub 1. So basically, result number 3 is telling us that proportional sa x sub 0 minus x sub 1, actually hindi pala technically proportional kasi this guy is not a constant because it will depend on the value of n. So the error on the nth iteration is a factor of how far your initial guess is to the first iterate. x sub 0 minus x sub 1. Okay? Though posibleng malaki tong x sub 0 minus x sub 1, don't worry about that if that is very big. Kasi posibleng nag-start ka sa isang malayong x sub 0 mula dun sa root. So yung x sub 1 mo, posibleng malaki yung leap from x sub 0. Right? Pero don't worry because yung lambda to the power n will take care of further minimizing the error. Kasi yung lambda nga is a number that is less than 1. If you raise it to a large enough power, this will decay very fast. Tapos i-divide pa natin siya by 1 minus lambda. Okay? So this is a nice error estimate for the fixed point iteration. And actually this tells us na yeah, paliit ng paliit really yung error kasi nga yung habang palaki ng palaki si n, dito pa lang sa numerator na to, lambda to the power n, lambda being less than 1, that will decay to 0 fast. Okay? Kaya lang, I don't want to get your hopes up because of result number 4, which tells us one thing. All right? So can anybody tell me what equation 17 tells me about the rate of convergence of the fixed point iteration? So this is telling me that the limit of the ratio between the error on the n plus 1 iterate all over the error on the nth iterate is equal to f prime of p. This guy is a constant. It is the function value of the derivative at the fixed point p. Pero I hope this reminds you or this rings some bells, all right? So ano yung ibig sabihin nito? Ano yung ini-imply niya? Of course, i-imply niya yung 3.18, yeah? But yes, CK, ano yung ibig sabihin ng equation 17?
Is it the asymptotic error constant po?
Okay, yeah. You can say that. Thank you, CK. That's right. The asymptotic error constant is f prime of p, which is the constant. Yeah, that's correct, but I'm looking for the other thing. Ito siguro yung mas significant. Anyone else? Ano pa yung sinasabi ng equation 17 aside from giving us the asymptotic error constant? Ano pa yung message ng equation 17? Anyone else? CK, baka alam mo rin. Ano pa yung sinasabi ng equation 17? Okay, wala nang gusto mag-try. Well, equation 17 is telling us one more thing, okay? That the rate of convergence of fixed point iterations is linear, okay? Kasi nga, di ba, ang fixed point iteration, titingnan mo ano yung power nung nasa denominator. The denominator has power 1. So this tells us that the fixed point iterations, assuming that the premises of the theorems are met, of this theorem are met, has rate of convergence equal to 1, so linear convergence with asymptotic error constant f prime of p. So mabagal din siya. Mas mabagal siya sa secant, mas mabagal din siya in general sa Newton-Raphson. Okay? Yung Newton-Raphson kasi special case siya kasi yung fixed point yung iteration ng Newton-Raphson involve yung derivative ni f. Okay? So that means hindi lang si f at saka si f prime yung continuous. Si f double prime din yata dun sa conditions ng Newton-Raphson dapat maging continuous. Okay? Kasi kinuha natin yung Taylor series expansion niya up to the second order. Pero dito sa contraction mapping theorem, ang ginaguarantee, ang nire-require lang natin ay yung continuity ni f at saka ni f prime. So if these conditions are met, then we will have an iteration that converges to the unique fixed point and that it converges linearly. And as n increases, all right, habang lumalayo ka ng lumalayo dun sa iteration, now we can estimate the error. The error on the n plus 1 iteration is equal to the derivative of f evaluated at the fixed point times the error in the previous iteration. So ito yung isa pang error estimate. Okay? Now, of course, theorem equation 18 might not be very helpful or in practice Bakit? Kasi hindi nga natin alam si P, right? So hindi natin mako-compute si F prime of P. Kahit alam natin approximately equal siya dun sa F prime of P times the previous error. But the problem is we don't know P, so this might not be very helpful unless you can find a bound. Pwede mo itong gawing less than or equal to sa M times P times X minus, times P minus X sub N, where P is your root, is your fixed point. Okay? Kaya lang problematic pa rin pala kasi hindi nga natin alam si P. Okay? But just a spoiler, whenever you are dealing, if you want to look at F prime at P, kasi yun din yung makikita natin sa mga results later, but we don't know what P is, all right? Kasi nga yun yung sinosolve natin. So yun yung nangyayari in reality. Most of the times what we do is to estimate the maximum for the magnitude of F prime. So yun naman yung sinasabi ng contraction mapping theorem. Pwedeng tingnan mo na lamang yung maximum nung magnitude ni F prime. Because usually we don't have access to the function value of the derivative at the fixed point P. All right? So we will not prove this. Sabi ko nga, usually pinuprove to sa mga graduate courses na. I met the contraction mapping theorem. Siguro nung 175 nakita ko na siya pero fixed point theorem yata yung tawag namin. Hindi rin namin siya pinprove. When I took my when I took an applied analysis course, saka pa lang namin pinprove yung fixed point iteration. Okay? So, hindi ko na siya ipoprove, hindi ko rin siya ipapaprove sa inyo. So, let's just appreciate CMT by its results. Maganda, marami siyang results na binigay sa atin. And one of them is equation 19. Ito yung manggagaling dun sa proof ng theorem. Okay? But basically, we know the idea here. Pinalitan ko lang yung F prime of P at yung sinasabi ko kanina na pag hindi mo alam yung F prime of P, pwedeng palitan mo lang siya ng maximum magnitude nung function, nung derivative, right? Which we called lambda in the theorem. So equation 19 is another good error bound. Error bound to kasi less than or equal. Alam natin na hindi lalampas yung error dun sa right-hand side. Etong nasa equation 18 is an error estimate. Kasi approximately equal yung nakalagay doon. So I hope you are learning the nitty-gritty of this terminology. So hindi natin usually ini-interchange yung error estimate saka error bound. Okay. Now, medyo mahirap gamitin yung fixed point, yung contraction mapping theorem. Bakit siya mahirap gamitin? Mahirap siyang gamitin kasi ang dami niyang requirement. Okay lang sana yung F and F prime being continuous. But the bigger problem with the use of the contraction mapping theorem is that we need to make sure that F is a function from AB to AB. Dapat yung function values ay naninirahan din dun sa closed interval AB. And usually, it's very hard to find an interval AB kung saan nanggagaling yung mga x's na pag pinlog in natin siya kay F, ang sagot nandun pa rin sa closed interval AB. Alright? So mahirap maghanap talaga ng interval AB na yon. But that is the requirement before we can proceed to the conclusions of the contraction mapping theorem. Now, thanks to some mathematicians, merong alternative, yung mga practitioners. Ano yung mga pwede nilang gamitin? Kasi ang hirap i-guarantee or i-satisfy yung premises ng CMT. Now, for that, we will use corollary 3.1. Okay. Ano yung sinasabi ng corollary 3.1? Well, okay. Same conditions, but this time we are looking for the continuity of F and F prime on a closed interval CD. And that CD contains a fixed point of P. Now, dito sa corollary 3.1, nawala yung condition na dapat yung function natin ay from a closed interval AB to a closed interval AB. Okay? Nag-consider ako ng mas malaking interval. Kung saan kailangan ko lang dun sa malaking interval na yon, sure ako na continuous si F at saka si F prime, and at the same time, meron akong fixed point doon sa function na yon. So, it's not hard to satisfy the premises kasi nga, kung gagamitin mo siya sa root finding, pwedeng gawin mo ay i-plot mo siya, i-graph mo siya. Humanap ka ng isang interval kung saan merong root. Kasi nga, madaling i-translate yung paghanap ng fixed point sa paghanap ng root, right? Equate mo lang yung x equals f of x, tapos kunin mo yung x minus f of x, equate mo kay 0, root finding na siya. I-plot mo yung x minus f of x on a good window, Pag may nakita kang x-intercept dun sa graphing software mo, then sure ka na meron siyang fixed point si f, which is the root of x minus f of x. Now, kung contraction mapping theorem lang yung gagamitin mo, kailangan dapat yung interval AB, dapat ang function values ng mga x's na nandun sa closed interval AB ay nandun din sa closed interval AB, which is hard to find, especially if you are having a very large window. Okay? Pero thanks to corollary 3.1, well, as long as you know that you have a fixed point P, and then you have a large enough interval on which the fixed point belongs and where f and f prime are continuous, then pwede nating magamit yung conclusions ng contraction mapping theorem. Ano lang yung requirement? The requirement is that the derivative of f must be less than 1. The derivative of f evaluated at p must be less than 1. All right? Then, if that is the case, then we are sure na may nag-exist na interval AB around P for which the premises of the contraction mapping theorem holds. So, nag-start ka sa isang malaking interval kung saan continuous si F at saka si F prime, tapos na meron dong fixed point. Kapag yung derivative evaluated at P has a magnitude less than 1, then sure tayo may nag-exist na interval AB na nasa-satisfy na yung premises, and so, pati yung conclusions ng contraction mapping theorem. So, hindi mo na kailangan maghanap ng interval AB kung saan yung function ay mapping from AB to AB. Alright? Pwedeng mas malaking interval yung i-consider mo as long as sure ka na mayroong fixed point nun and the derivative of f evaluated at P has magnitude less than 1. Okay? Tapos lahat na nung results sa contraction mapping theorem ay mag-hold. Okay. So, ito yung crucial thing. And again, just a spoiler, nasabi ko na pala to kanina, so na-spoil na kayo. Kapag wala kayong access kay P, pwede nyo na lang kunin yung maximum ng F prime over that interval. Kung sure kayo na yung derivative ay hindi lumalampas ng 1 sa kahit anong x, then sure na kayo ng F prime of P ay magiging less than 1. Okay? Yun yata yung gagamitin nyo sa lab exer on Monday. Kasi nga hindi natin alam yung root. All right? Now, there is another nice conclusion from Theorem 3.1. Okay, it says here that if G prime of P is greater than 1, actually, typo ulit. Dapat to ay F prime. Let me just mark it para edit ko yung handout. If the magnitude of F prime of P is greater than 1, then the fixed point iteration will not converge. Okay? Hindi magko-converge ito kay P. Posible mag-converge siya sa isang number, pero hindi siya magko-converge sa fixed point. Dun sa fixed point. Alright? Kapag yung derivative ay mas malaki kay 1. If the derivative is equal to 1, no conclusions can be made from corollary 3.1. Pero kapag yung derivative ay equal kay 1, posible siya mag-converge dun sa fixed point, pero super bagal. Sinuwerte ka na mag-converge siya, pero mabagal yung convergence that is to the point na impractical na siyang gamitin. So that's why usually ginagamit natin yung fixed points pag sure tayo na si function f ay isang contraction. All right? Meaning the derivative is always less than 1. Okay? Now, ito yung mga concepts na kailangan nyo. And as I have mentioned, pwede nyo siyang gawin sa spreadsheet or madali lang din naman siyang i-code kay MATLAB or Python. Just use a jump, unsuggested halting criterion ay jump-based. So, kunin yung relative error or the relative jump between two approximates. So, yeah. I'm thinking I might need to borrow 10 minutes. Okay lang ba sagad ko ng 1 p.m. para matapos natin siya? If you need to leave early, then that's fine. You can just watch the recording. Gusto ko lang siya talagang matapos. Konti lang naman yung daldal ko ngayon, no? Ba't hindi ko pa rin siya natapos? Anyway, so yeah, example 3.6. Babalikan natin yung mga fixed point iterations natin kanina. Tapos titingnan natin kailan siya nagko-converge o sino sa kanila yung mga nagko-converge. Tapos, i-implement natin siya or in-implement ko siya sa isang spreadsheet. Now, remember yung mga examples natin kanina, yung function f, g, h, and j. Sila ay mga fixed points nila si square root of 5. All right? And then I can use this fixed point iterations to solve this quadratic equation x squared minus 5. Kasi ang solution nito ay si plus or minus root 5. Okay? Now, luckily, alam natin yung root, so pwede natin gawin talaga yung analysis kanina. So ang root niya ay plus or minus 5, which is plus or minus 2.23 or plus or minus 2.24. Tapos balikan natin yung mga nandun sa example 5. Okay. Una, tingnan natin yung unang fixed point iteration, yung function f. Paano nakuha yung fixed point iteration na f? Kanina yung mga classmates nyo sinabi kung paano mag-solve ng fixed point. Ngayon, paano tayo mag-iimbento ng fixed point iteration para ma-solve ang isang root finding technique? Now, the problem here is finding the root of x squared minus 5, which you might say, napaka-simple sir, alam natin yung solution yan. Pero for illustration purposes and for analysis purposes, maganda siyang example. Alright? X squared minus 5 equals 0. Ito yung kailangan kong hanapan ng solution. Ito yung root finding problem. Now, if I want to solve this using a fixed point iteration, then I need to define a fixed point iteration of the form this guy. Okay? Paano ako makakahanap ng fixed point iterate? Paano ako makakahanap ng function f? Now, I'll just play around and do some algebraic manipulations to x squared minus 5 equals 0. Okay. So, copy ko yan over. And then, ano yung nangyari? Nag-multiply ako both sides by a negative 1. And then, after this, I added x to both sides of the equation. So, and then, ultimately, I got this. X equals 5 plus x minus x squared. Tapos, ito yung sinabi kanina na, yeah, kaya ako nasabi na yung square root of 5 ay fixed point nung 5 plus x minus x squared. Okay? So starting from the equation that you want to solve, play with it, be creative with it, do some algebraic manipulations to get a fixed point of the form x equals something or x equals a function of f. Okay? Ganito ko nakuha yung nandun sa una nating example. Okay? Now, what is the fixed point iteration? The fixed point iteration is x sub n plus 1 equals the function value at x sub n. And we are free to choose whatever initial condition we want. Okay? Ang tanong, magko-converge ba itong fixed point iteration na to? Kasi sabi, kapag ka na-satisfy niyo yung premises ng CMT o premises ng corollary 3.1, alam natin magko-converge siya for any x sub 0. Alright? Pero unang tanong, magko-converge nga ba siya? Now, to see whether it will converge or not, we can take advantage of corollary 3.1. Kailangan ko lang tingnan yung f prime at the fixed point. Okay? So, computing the derivative, makukuha niyo 1 minus 2x. Luckily, in this example, we know what p is. We know that square root of 5 is a fixed point ni f. So, ang gagawin ko, plug in ko si f prime. Plug in ko si root 5 kay f prime. And what I'll get is this number, which is less than negative 1. So yung absolute value ni f prime of root 5 ay greater than 1. So definitely, kahit ano pa yung piliin kong initial condition, this iteration will not converge to root 5. Similarly, it won't converge to negative root 5 also kasi yung derivative at negative root 5 will also have a magnitude greater than 1. Kung ayaw nyong maniwala sa corollary 3.1, sige, gawin natin sa Excel kasi madali lang namang i-program sa Excel yung 5 plus x minus x squared. And the results I have is in figure 3.7. Isa-isay natin. Okay? Yung root natin ay around 2.34. So initial guess ko ay 2. Ginamit ko yung fixed point iteration for f. Ito yung nakuha ko. Alright? And you see that hindi talaga siya nagko-converge kasi alternating yung sign, no chance that this will converge. Let's try another one. 2.1 halimbawa. For 2.1, lalong hindi siya nagko-converge. Look at the result at the 10th iteration. It's 6.37 or negative 6.37 times 10 to the 79th. So it looks like this will converge to negative infinity, yung fixed point iteration if I start at 2.1. Now, sige, 2.2. Palapit ako ng palapit dun sa actual root para makita, baka naman pagka malapit siya dun sa actual root, mag-converge siya. Pero 2.2 na to, negative 1.1 times 10 to the 40th yung nasa 10th iteration. So mukhang yung fixed point iteration na to will diverge again to negative infinity. Tapos isa pa, sige nga, 2.23606. Diyan ako nag-start. Napakalapit na niyan dun sa positive root 5. Pero you see here, okay, mukhang nagko-converge siya, pero biglang 6 iteration, medyo lumayo. Tapos nag-start na siyang lumayo, nag-fluctuate yung value. 10th iteration, negative 0.032929 na nakuha ko. So there is a very erratic behavior. At least the 10 iterations are suggesting na hindi siya magko-converge. Pero dapat in-expect na natin to. Dapat hindi ko na ginawa yung figure 3.7. Kasi nga alam ko na, by just looking at f prime of root 5, hindi na talaga magko-converge yung fixed point iteration kahit ano pa si x sub 0. Alright? So that's that. Okay. Let's look at the second fixed point iteration. Yung fixed point iteration kanina ay 5 over x. Ito si g kanina dun sa example natin. So alam natin si root 5 ay fixed point ni g. Okay. Let's see if how did we get g? All right. So start ulit ako dun sa equation na gusto kong i-solve. Manipulate ko lang yan. I'll add 5 to both sides. And then I'll divide both sides by x, assuming that x is not equal to 0. I get this. So ang form nito ay x equals g of x. So this is a fixed point iteration if I will compute x sub n plus 1 to be the function value of x sub n under g. Okay, so fixed point si g, hoping that this will converge to the fixed point root 5 of 5 over x. However, if we plug in plus or minus root 5 into the derivative of g, ito si g, so ang g prime ay negative 5 over x squared. Pag pinlagi natin si plus or minus root 5, ang sagot ay equal kay 1. So hindi mag-apply si corollary 3.1 kasi naging equal kay 1 yung derivative. Pero pag inanalyze nyo ng konti, pwede nyo itong gawin sa Excel or pwedeng mano-mano nga, makikita nyo na hindi na talaga ito mag-converge kasi ito ay magiging alternating sequence. Bakit? Kasi, halimbawa, nag-start ka sa x sub 0. So si x sub 1 ay g of x sub 0. So that's 5 over x sub 0. That's fine. Then x sub 2 is g of x sub 1. So that's going to be 5 over x sub 0. 5 over x sub 0 nga. Okay. So this guy will be what? Tama bang iteration ko? 5 over x sub 0. Tapos, para makuha si x2, g of x2, g of x1. Yeah. Maging 5 over x sub 0. So ito ay magiging... Bakit na-loss ako pagko-compute? Yeah, this will become x sub 0. Cancel yung 5s. Okay. Tama ba? Yes. Tapos, x sub 0 na ulito, no? So, ibig sabihin si x sub 3 ay g of x sub 2, which will be g of x sub 0. Okay, kasi ang x2 ay x sub 0. G of x sub 0 is again 5 over x sub 0. So, si x4, x sub 0 ulit. Si x5 ay 5 over x sub 0. Si x6 ay x sub 0, and so on. So magkakaroon ka lang ng nag-alternate lang between two values, namely 5 over x sub 0 and x sub 0 yung results ng iteration. And therefore, this will not converge. Okay? So, yeah, this is an example na equal kay 1 yung derivative pero hindi siya nag-converge. So far, no luck yet. Yung dalawang fixed point iterations na dinefine natin ay hindi nagko-converge. Let's try the function h. Okay, hindi ko tanda kung ano yung function h. Tingnan na lang natin kung ano yung ginawa, paano siya dinerive. Again, we start with the equation we're solving. Tapos, anong ginawa? Nag-divide lang ako ng negative 5 both sides. Kaya ako nakuha to. Walang nangyari sa right side kasi 0 siya. So, okay lang mag-divide ng negative 5. And then, nag-add ako ng x to both sides. So, nakikita nyo paano nagiging creative rito. So as long as you're doing valid algebraic manipulations, then that's fine. So nag-add ako ng x both sides. Tapos here, I just what? I think I just manipulated this, combined like terms, and I got this one. 1 plus x minus x squared over 5. So, and then I can call this h. Okay. So now I have the fixed point formula x equals h of x, and I can define the fixed point iteration x sub n plus 1 equals h of x sub n. Okay. So kita nyo, dapat kailangan nyo lang mag-imbento ng valid algebraic manipulation na gagawin dun sa equation na sinusolve nyo. Okay. And here we will be lucky because if we compute for h prime, and then plug root 5 in, okay, we'll get 1 minus 2 root 5 over 5, which is approximately 0.106, which is less than 1. Okay. So by corollary 1, since the derivative is less than 1, and then if you plot x squared minus 5, makikita nyo na meron siyang x-intercept as long as you plot it on a large enough interval. Then corollary 1 tells us that there is a small interval near the fixed point kung saan siya ay magko-converge. Okay? Kailangan nyo lang piliin si x sub 0 to be close to your root. Okay? Kasi nga dapat piliin mo yung x sub 0 to be anywhere in a closed interval AB. Ang problema rito, usually, hindi natin alam kung ano yung closed interval AB. So to be safe, try to pick a starting value that is close enough to the fixed point h. Okay, so now we're good. We know that this fixed point iteration will converge. Okay. However, if you compute for h prime of negative root 5, okay, kasi nga ito pa yung isang root, yung derivative at negative root 5 will have value greater than 1. So, ibig sabihin, hindi siya magko-converge kay negative root 5. So, makakagawa ka lang ng isang fixed point iteration that will converge to root 5. Kasi nga, hindi niya kayang mag-converge kay negative root 5 kasi ang derivative at negative root 5 ay greater than 1. Okay? Now, I implemented this fixed point iteration, and that's in figure 3.8, using several values for the initial guess. Okay? Kasi nga sabi nito ay basta maliit yung basta malapit yung x sub 0 kay p, though wala tayong characterization gaano kalapit is malapit. Alright? So, let's just do trial and error kasi isang Excel drag lang naman ito, ano? So x sub 0 equals 2, well, we get 2.23 after the 10th iteration, and that will have relative error of around 2.81 times 10 to the negative 11. That's very good, right? Remember, the relative error is computed as x sub n minus root 5 over root 5. Siya yung relative error. Ilang percent yung error niya mula dun sa square root of 5 na kinocompute natin. So maganda, 10 iterations, 10 to the negative 11. That's a pretty remarkable result. Okay? Sige, ilayo ko ng konti. Hindi pala ilayo ng konti. Todo ilayo ko yung root. Di ba ang root ay 2.34, around 2.34. Gawin kong 5 yung initial guess. Now, even if I put 5 as my initial guess, on the 10th iteration, look at the answer I got, 2.236. Correct up to 3 decimal digits or even more. And actually, the relative error is 10 to the minus 9, order 10 to the minus 9. Tapos try ko na malapit, 2.23606. Dun sa 10th iteration, na-surpass ko na yung machine precision, usually ng mga computers. Times 10 to the negative 16 na yung error. Right? When we say machine precision ng computers, usually when doing computations, yung 10 to the minus 16 is considered 0 na by our computing devices. Okay. Now, pag nagsimula ako sa negative root 5, okay, ito yung kagandahan. Di ba nakita natin kanina na hindi ito magko-converge sa negative root 5. Magko-converge lang yung iteration sa positive root 5. Kasi yung derivative at negative root 5 has magnitude greater than 1. Tinry ko lang, out of curiosity, ano yung mangyayari kapag nag-start ako sa negative root 5 or somewhere close negative root 5. Magko-converge nga ba siya sa negative root 5 or the iteration will find a way to reach positive root 5? And true enough, after 36 iteration, nakuha ko yung positive root 5. So ibig sabihin, guaranteed talaga na siya ay magko-converge, alright, dun sa fixed point kung saan yung derivative ay may magnitude na less than 1. It might take lots of iterations, but it is guaranteed to get there. Okay? Now, I'm leaving you as exercise yung pag-a-analyze kay G. Try to practice with it and see paano ko nakuha si J. So, start ka sa x squared minus 5. Paano ko nakuha yung 1/2 x sub n plus 5 over x sub n. Okay? Tapos, hold on. Kalimutan kong banggitin. Ang h prime of root 5 dun sa example kanina ay equals to 0.106. So, ito yung asymptotic error constant. So, ibig sabihin at every step of the way, the error is decreased by approximately a factor of 0.106. Tingnan natin kung apparent siya dito. So, 0.106 around nababawasan ng isang order. So look at this one. Order 10 to the minus 6, dahil lang asymptotic error constant ay order 10 to the minus 1, it's 0.106. Then yun, nabawasan ng isa yung order of magnitude dun sa relative errors. Okay? And this will happen for large enough n's. So dito, hindi pa siya nabawasan ng mga 1 degree or 1 order, pero pag nag-start na siyang lumaki si n at n equals 6, n equals 7, it's 1 degree less. 10 to the minus 6 na siya. N equals 8, 10 to the minus 7 na siya. N equals 9, 10 to the minus 8 na siya, and so on. And that is to be expected because the asymptotic error constant is about 106 or 10 to the negative 1. So yung error dapat at every iteration nababawasan ng factor 10 to the negative 1 for large enough n's. And you can see that here in our tally of the relative errors. Kahit dito, no? So, ang bagal nung pagbaba ng relative error, pero para siyang diesel. Pag nag-init na yung fixed point iteration, starting at say the 26th iteration, okay? 10 to the minus 5 na yung error, the asymptotic error constant will kick in kasi large enough na si n. Nabawasan na ng 1 order yung relative error, nabawasan na siya ng 1 order, and so on. Okay? So I think that's it. Sorry, overtime na talaga, 1:03 na. Do you guys have any questions? So exercise na lang yung sa J. Meron naman dyang instructions. And then, any questions? If none, tatawad pa ako ng possibly 2 or 3 more minutes para bigyan kayo ng konting hint sa exercise. But before that, questions? Oh, thank you for staying with me. Marami pang natira. Okay. All right. So if you have no questions right now, that's fine. And as Charles mentioned, kung may questions, chat nyo na lang ako. All right. Or sa Monday sa laboratory. Okay. So I think we are ready to finish Lab Exer 1.2. So the laboratory exercise on Monday, Lab Exer 1.2 Part B, we will cover the rest of the problems from exercise 1.2. So kasama na si B, tapos kasama na rin si number 2. So tatapusin na natin yung Lab Exer 1.2. Okay? Now, dun sa problem number 2, binigay ko yung equation na hanapan nyo ng solution. X minus arctangent of x equals 1. Tapos, ang medyo challenging to kasi paghanapin ko kayo ng dalawang fixed point iterations. Well, finding fixed point iterations might be easy kasi una, ito yung equation, agad-agad. Alam niyo na si x equals 1 plus arctan x ay isang fixed point iteration. Okay? Or pwede ko siyang gawin, kaya ko siyang i-define as the fixed point iteration, right? Kaya lang ang challenge sa part A, dapat bigyan niyo ako ng dalawang fixed point iterations. Yung isa dapat ay convergent, tapos yung isa dapat ay divergent. So dalawa yung ibibigay niyo. Yung isa sure tayo na convergent, yung isa sure tayo na divergent. And you need to show the convergence analysis for both iterations. What I mean by convergence analysis is what we did in the easy examples we did earlier. So tingnan nyo lang yung derivative nung function defining your iteration. Okay? Ang kaibahan nga lang dito, halimbawa, pag kinuha mo pag nag-define ka rito ng fixed point iteration, posibleng may mga arctan, posibleng may arctangent, posibleng may tangent, and so on, whatever crazy function you want to incorporate with it. Pero ang problema, hindi natin alam yung solution nito. Remember, in the analysis we did earlier, we plug in the fixed points into the derivatives kasi alam natin si root 5 ay fixed point. Ang problema rito, posibleng hindi natin alam kung ano yung solution ng equation na to. So hindi natin alam yung fixed point na hinahanap natin. So what you can do is, pag nag-define ka na ng x sub n plus 1 equals say f of x sub n, alright? Tapos kukunin mo yung f prime, right? Wala tayong way para ma-compute yung f prime of p. Kasi nga hindi natin alam kung ano yung solution ng equation na to. Yun nga yung hinahanap natin. But what you can do instead is look at ano yung bound para dito. Okay? And I guess at least for the two examples that I used in the two functions that I used in the answer key, madaling i-analyze yung f prime. Napakita ko na yung f prime ay laging less than 1 at saka yung f prime ay laging greater than 1. So you can analyze what will happen to f prime for all x's. Okay? So nasabi ko dun sa napili kong fixed point iteration dun sa answer key na looking at f prime, siya lang naman ay 1 over 1 plus x squared, lagi siyang less than 1. Parang ganon. So hindi ko kailangan malaman ano yung root kasi alam ko na yung behavior ng f prime for whatever x's you plug in into it. Okay? So, and then this is what is usually happening in applications. Hindi mo ma-check yung f prime of p kasi nga hindi mo alam si p. Pero kung alam mo yung bounds para kay f prime, then you can definitely do a convergence analysis. Okay? And I think that's it. Thank you guys for indulging me 10 minutes or so. All right. So, questions? So kung wala na, so let's see each other in the labs on Monday. All right. So just send me your questions. But until then, keep safe, everyone. Enjoy the weekend and see you on kailan nga? Wednesday. Yung D2L, see you on Monday. Bye, guys.
Thank you, sir.
All right. You're welcome.
Thank you po, sir.